Alright, Levi, you're in the shot a lot, just so you know. So behave, otherwise, we'll see what happens. Yeah, sorry about that. And I lost my marker.
It's a constant.
Just make sure okay, yeah, it's going. And maybe shut that door. I have to have this one back a lot further, so. Might be worse at picking up my voice because Jared's so loud. Alright. So let's begin. Ignore the stuff on the right hand board. That's calculus stuff. And we'll erase it again.
It's a lot like ours.
Yeah. Proving stuff. This is a great prereq for how I teach calculus. Anyways, smallest counterexample. How does smallest counterexample work? Smallest counterexamples are proof by contradiction. But they're a special kind of proof by contradiction that utilize a property that the natural numbers have. Now, remember in this class at the beginning, we kind of said, I'm going to just assume that you know what the integers are and what the natural numbers are, and we didn't come up with good definitions for what we mean by these things. Right? We had to assume some starting point, and one of the starting points we assumed is you kind of already know what the natural numbers are and the integers are, and we're just going to use them. You remember that discussion? You're with me? Still zoning in? Lost? You're with me. All right. So if we were to develop the natural numbers from the beginning and define them, no matter how we define them, we would either make so that they had this property by definition, or we would prove that they have this property. So no matter how you create the natural numbers in earlier math, more fundamental math, I should say, they're always going to have this property, which is a pretty intuitive property. So it's every non-empty set of natural numbers contains a least element. Right? And that should make pretty intuitive sense. And of all the sets that we talked about, the natural numbers are the only one that has that. The integers don't have that, the rationals don't have that, the reals don't have that. So it's a special property that the natural numbers have. Every set of natural numbers has a least element. And that's the property that we're going to utilize in smallest counterexample. Kind of makes sense. Least element, smallest counterexample, and those two are very connected. So I think the best way to get a feel for how to do these types of proofs is to just see an example. I'm going to be a lot more explicit than the author is in the book with how we're using this property. He kind of does it weird, going and like trying to give you intuition for how to think about it, and then comes back and says, oh, and by the way, you were using this behind the scenes, and here's what the proof would have actually looked like. I don't like that he does that. So, just get introduced to you directly and use the property directly. So let's see an example of a proof like this. So we're going to prove that every natural number is either even or odd. Okay? So, first I define this set of numbers that don't have that property. So let x be the set of all natural numbers that are neither even nor odd. So x is a set of all natural numbers n, where n is not even and n is not odd. Now we know that this is an empty set. There's nothing in there.
Right.
So this is how you start these out. Define a set that you know has nothing in it, and then here's a contradiction. Here's where we assume contradiction. Assume by way of contradiction that x is not empty. Okay? In other words, that there is some natural number in here. Okay? With me so far? So now, if this thing's not empty, then it's a non-empty set of natural numbers, which means it has a what? A least element, using the well-ordering principle. So then by the well-ordering principle, big X contains some least element, call it little x. Okay? So this is the smallest natural number that is neither even nor odd. Any natural number smaller than this thing has to be both even, or has to be either even or odd, right? Keep track of what that x is. So big X here is a set of all natural numbers that are not even and are not odd. X is the smallest thing in there. So it's the smallest natural number that's not even and not odd. So if I get a natural number smaller than x, it's either even or odd.
Oh, all right, okay.
You with me?
Yeah, that makes more sense.
Okay.
Make sure that that click makes sense. That's where you're going to get stuck on this over and over again.
Right.
Is making that click. Here's a set of everything that doesn't have the property. Here's the smallest thing that doesn't have the property. Any natural number smaller than this does have the property. And we're going to use the fact that the thing smaller than this, we're going to use the idea that the thing smaller than this has a property to show that this also has a property. So we say this is the smallest thing without the property. We're going to show that something smaller than it having the property means it has a property. Therefore, it doesn't have the property and it does have the property. Contradiction. I'll say that one more time when we go through it. I'm trying to give you a big picture where we're going, but maybe let's just go through it and then we'll go from there. So x is the smallest thing that doesn't have the property. So any natural number smaller than x does have the property. First thing I need to do is make sure that there is a natural number smaller than x. Or in other words, make sure x isn't 0. Okay? Since 0 is even, x isn't 0. Good? Right. Since 0 is even, x can't be 0. Remember, x is the smallest natural number that isn't even and isn't odd. We know that 0 is even. So x can't equal 0.
Okay.
Since x is a natural number, x must be greater than 0. Then, x minus 1 is greater than or equal to 0.
Right.
Wait, why?
So x is greater than 0. So x minus 1 is greater than or equal to 0. So look, if x can't be 0, what's the smallest thing it could be?
1.
1. 1 minus 1 is 0.
Right.
You with me?
Yeah.
So since x has to be greater than 0, x minus 1 has to be greater than or equal to 0. In short, x minus 1 is a natural number. That's all I was trying to get. A smaller natural number than x. Here's x. I needed a smaller natural number than x. X minus 1. Now, since x is the smallest element that is not even and not odd, then x minus 1 is either even or odd.
That's so tricky, Ken.
I know, it's really weird to begin with.
Oh, okay.
So, you'll get confused and you'll be like, oh, I get it. Then you'll be like, oh, wait, I don't get it. Oh, I do get it. That will happen a few times, so make sure you're following along as we do this. So, x minus 1 is smaller than x. X minus 1 is a natural number. X was the smallest natural number without these properties, so x minus 1 must have those properties. It must be even or odd. Okay, if x minus 1 is even, then there exists some integer a such that x minus 1 equals 2a, or x equals 2a minus 1, which equals 2 times an integer plus 1. So x equals 2 times an integer plus 1, which means x is odd. So that's not looking good, but maybe x minus 1 was really odd.
Right.
So if x minus 1 was odd, then there must be some integer b such that x minus 1 equals 2b plus 1, or x equals 2b plus 2, or x equals 2 times b plus 1, making x even. So either way, x is even or x is odd. Contradiction. Therefore, x is even or odd. Contradiction. X was the smallest number that wasn't even or odd, which means x minus 1 had to be even or odd. But if x minus 1 was even, x was odd. If x minus 1 was odd, x was even. So x was even or odd. You see the contradiction? It's kind of a weird way of doing these contradictions, but it's really powerful. So there's our contradiction. Therefore, the set x is empty. Right? We assume by way of contradiction that it wasn't empty, therefore it is empty. Or in other words, all natural numbers are either even or odd. There are no natural numbers that aren't. Good? Okay.
That's cool. What is that?
That's called proof by smallest counterexample. Alright. Yeah, so x was the smallest counterexample. X was the smallest thing that made this statement not true. Which could exist. So So it's a type of proof by contradiction. Sorry, I was using my iPad, so I lost where I was. And every integer is either even or odd. That's pretty easy. So now we're going to prove every integer is either even or odd. Remember, over here we just proved it for natural numbers. Now let's prove it for integers. Okay. Every integer is either even or odd. Let x be some integer. Now we have two cases. X is greater than or equal to 0, or x is less than 0. We need to show either way x is even or odd.
Oh, okay.
You with me?
Yeah.
Okay. So if x is greater than or equal to 0, and it's an integer, then it has to be a natural number, right? And so it's either even or odd. That's what we just proved. Every natural number is either even or odd. Oh, sorry, down here. Now let's look at the other case. If x is less than 0, then negative x is a natural number. Pick a number smaller than 0. Pick an integer smaller than 0. Is negative 2 a natural number?
Yes.
Yeah, it's 2.
Negative 2.
Is 2. Is a natural number.
Why is it negative?
Yeah.
So why is there a negative?
How else do I say it? If x is less than 0, or in other words, if x is a negative number, then negative x is a natural number.
Okay. It's like saying if negative 2 is a negative number, then negative 2 is a positive number.
Exactly.
Right. Exactly.
That's so dumb. You can't just do that.
Why?
Because you're working with negative 2, not positive 2.
Well, we'll say something about positive and negative 2, so we'll come back to x. So just follow the logic so far. So if x is less than 0, if x is negative, then negative x is not negative. So it's a natural number, right? And since negative x is a natural number, negative x is even or odd. If negative x is even, then there is some integer such that negative x equals 2a, which gives x equals 2 times negative a, is even. So x is even. See it?
Yeah.
And same thing. If negative x is odd, then there's some b such that negative x equals 2b plus 1, which gives x equals 2 times negative b minus 1. If you don't see what I did there, I multiplied both sides by negative 1. Good?
Yes.
And then I'm going to add 1 and subtract 1 and combine the negative 2 right there. So we have negative 2b minus 2 plus 1 is the same thing as negative 2b minus 1, which is odd. So x is either even or odd, no matter how you look at it. So we had to use the fact that all we knew about was the natural numbers to prove it for the integers. Good? All right. Let's continue then. Let n be a positive integer. The sum of the first n odd natural numbers is n squared. So, in short, what we're saying is, we're saying 1 plus 3 plus 5 plus ... plus 2n minus 1 is equal to n squared, or, better way to write it, the sum from k equals 1 to n of 2k minus 1 is equal to n squared. Understand what we're trying to prove? I'm going to use this notation instead of all that sloppy writing. Okay, so we're going to prove that this is true. And we're going to once again use smallest counterexample to prove it. Kind of a weird way to think about these. So 1, I'm going to make my set x just like I did before. let x, big X, equal the set of all n in n. Now obviously this is only true for n greater than 1, greater than or equal to 1. Right? So let's prove this for all n greater than or equal to 1. So let x be the set of all natural numbers where n is greater than or equal to 1, comma, well, and this is false. And then 2, we'll do the exact same thing we did on the other proof. Assume, by way of contradiction, that x is not equal to the empty set. 3. By well-ordering principle, x contains some least element little x. Okay? So everything up to there you should have kind of been able to just do on your own for proving this. This is the same basic setup that you do every time you're doing proof by smallest counterexample. So recap, what am I trying to do? I'm trying to show that 1 plus 3 plus 5, the sum of the first n odd numbers is equal to n squared anytime n is greater than or equal to 1. Right? So I'm going to let x be the set of all natural numbers greater than 1 that don't make that true. Assume that that set is not empty, and show that leads to a contradiction. And so the set has to be empty. So there are no natural numbers greater than 1 that make this false. So every natural number greater than or equal to 1 makes it true.
Okay.
I feel like I'm losing you guys, but I don't know.
We're paying attention.
Are you?
Yeah.
Yeah?
We got it.
We got it.
We're just waiting for the next step.
Okay. So, x contains some least element. First off, we need to make sure that x minus 1 is a natural number greater than or equal to 1. Same thing we did over here. We need to make sure x minus 1 wasn't 0. Or sorry, we need to make sure x wasn't 0, so that x minus 1 was a natural number. Here we need to make sure x minus 1 is a natural number greater than or equal to 1. So we need to make sure x doesn't equal 1.
No, it can equal 1.
It could.
Oh,
So far it could. So we need to show specifically that it can't be 1. So 4. Observe that 1 equals 1 squared, comma, and so x is not equal to 1. Right? In other words, 1 has a property. If you sum up the first 1 odd numbers, you get 1 squared.
What?
Alright, what is this set x? What is everything in here? It's all natural numbers greater than or equal to 1, such that when you sum up that many of the odd natural numbers, you don't get n squared.
Okay, wait. Oh,
I don't know another.
so 1 plus whatever's in that equals 1 squared, but we don't want to get that, so it can't be 1.
We now know that 1 is not in here.
Right.
Because 1 makes the statement true. If I add up from k equals 1 to 1 to k minus 1, I get 1 squared. Right? You guys are killing me. What's holding you up?
I'm trying to,
Talk out loud.
I'm thinking. And
What's weird?
I want to make sure that I understand what the equation is saying and what your big X is saying before I lose myself in the rest of it.
Okay, first off, do you understand this statement?
I think so.
This is saying the sum of the first n odd numbers is equal to n squared. So in other words, 1 plus 3 plus 5 plus 7 plus 9 is equal to 25.
Right.
The sum of the first 5 odd numbers equals 5 squared. So we didn't get the statement. Okay. Do we need these on examples?
I never said that I got it.
Let's start with 2. 1 plus 3 is 4. 2 squared, 4. 1 plus 3 plus 5 is 9. 3 squared, 9.
Right.
Wait.
Oh, sorry.
Oh, right. Okay.
Alright. 1 plus 3 plus 5 plus 7 is 16. 4 squared, 16. 1 plus 3 plus 5 plus 7 plus 9 is 25. 5 squared, 25.
I'm good with that.
Okay, so that's what this is saying, or that's what this is saying.
Right.
Same thing. If you sum up odd numbers starting at 1 to take the first n odd numbers, you get n squared.
Why isn't that? Okay, never mind. That makes sense. Okay. Yep.
So do we now understand what we're trying to prove?
Yeah. Well,
Okay.
Yeah, I knew that before. I got lost at the
One.
big X because for some reason in my mind I was trying to think that you were saying that's false, and I'm like, wait.
Okay, so now what's big X? Big X is all the natural numbers greater than or equal to 1 that make the statement false.
Right.
Hint, we already know ahead of time there aren't any. This is an empty set. Right? That's why we're going to assume by way of contradiction that it's not an empty set, and see that leads to an impossible worldview. Right?
Right.
Leads to some obviously false statement.
Yep.
Okay. So, big X, set of all the natural numbers greater than or equal to 1 where this isn't the case. Big X must contain some least element, little x. So little x is the smallest natural number, such that when you add up the first little x odds, you don't get little x squared. Okay?
Mm-hmm.
Wait a minute. So n is the number of
Odd numbers.
integers you have.
Yeah, it's how many odd numbers you list out. Slowly getting closer and closer. Alright. So we know what the equation's saying. We know what x is. Big X. Do we know what big X is?
Yeah.
It's the set of all natural numbers that this is false for. Right?
Right, okay.
Okay.
I went to on before. Here we go.
So we've got x is the small, little x is the smallest thing in big X.
Mm-hmm.
It's the smallest natural number that makes that statement false. And we check real quick, is it possible for x to be 1? Well, no, because 1 equals 1 squared. So we know that x isn't 1. So now the smallest possible thing x could be is 2, right?
Yes.
Which means that x minus 1, the smallest it could be is 1. So in other words, 5, then 1 is less than or equal to x minus 1 is less than x, comma. So x minus 1 is a natural number with x minus 1 greater than or equal to 1. That's a bonus. You good?
Wait.
Since x can't be 1, then the smallest x can be is 2. Which means the smallest x minus 1 can be is 1. So x minus 1 is greater than or equal to 1. And x minus 1 is a natural number. So x minus 1 is a natural number greater than or equal to 1. So x minus 1 makes this statement true.
So,
X is the smallest natural number greater than or equal to 1 that doesn't make the statement true. So x minus 1 has to make the statement true.
Oh, right.
And we're going to show that if x minus 1 makes the statement true, then x also makes the statement true. Our contradiction.
Right, okay.
You see in big picture how it all moves around?
Yes. I
Awesome.
just saw that one little step that x minus 1 means it is true because x is the smallest one.
Yeah, there you go. The whole reason we got the x. Okay. 6. Then the sum x minus 1 of 2k minus 1 is equal to,
Will it be equal to that, wouldn't it?
I don't know.
No, wait.
I have to get some markers to start checking. Oh, I got
Okay,
3 right
so
here.
3 comma,
I'm trying.
isn't it?
What does our statement say it equals?
N squared,
Which is?
K squared,
No.
X
squared.
minus 1 squared?
X minus 1 squared. Thank you.
No, that part of it. X minus 1.
And whatever's right there. Whatever's right there. However many you're adding up.
I'm missing how we got to that though.
Yeah, you like skipped a bunch of steps.
Yeah.
Well, how do we know that X
We
minus
knew
1
that
is
x minus 1 makes a statement true, right? So x minus 1 is the natural number that makes this statement true.
Okay.
So the sum of the first x minus 1 odd numbers equals x minus 1
Sorry.
squared.
I was trying to understand the steps, so I failed to connect that X minus 1 equals N for a second.
Okay. We good?
I still don't know how X minus 1 can be N though, because, I mean, it can be in N. Wait,
Well, this n is just any natural number you want to put there. I can put 5 there. So the sum from 1 to the sum of the first 5 odd numbers is 5 squared.
right, okay.
The sum of the first 50 odd numbers is 50
Oh,
squared.
it's so confusing.
The sum of the first x minus 1 odd numbers is x minus 1 squared. That's what the statement says. So are we good with all that now? We good with this statement?
Yeah.
Okay. So then, to get, well, I guess I can write one more line right here and then see it. 7.
Is that going to be on camera?
Then, huh?
Is that going to be able to be seen?
I think so. Why would it? Then the sum from k equals 1 to x of 2 to the k minus 1 is equal to,
X squared.
well, we don't know if it's equal to x squared yet.
It'd be X minus 1.
It's
squared
equal to-
plus 1.
X minus 1 squared. Maybe I'll write it this way. Maybe do a side note thing so that I don't lose you guys on this. If I want to do the sum from k equals 1 to 5 of, I don't know, k squared, then another way I could rewrite this is the sum from k equals 1 to 4, k squared plus 5 squared. Okay, if that's throwing you off and you really aren't comfortable with this notation.
I'm really not. This is.
Alright, so let's get comfortable. What does this mean? This means 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. What does this mean?
Oh.
1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared.
Okay.
So we pulled out the last element of the sum.
All right.
Okay?
Yeah.
So I'm going to do the exact same thing here. I'm going to pull out the last element. So I can rewrite this.
So then it's X squared plus.
The sum from k equals 1 to x minus 1 plus what we get when we plug in our last term x, which is 2x minus 1.
Okay, right.
You see that?
No.
The last term we get when we go from k equals 1 to x in this thing is 2x minus 1.
Why?
Because K goes
Same thing
up
here.
to X.
I mean, look, I could have done 5 minus 1 here.
Right. Right.
And then what we got when we plugged in 5 to that. Don't let what's up here confuse you. I don't know if that's throwing you off.
It's not. So this is saying, okay, the sum of k equals 1 to x of the odd numbers is equal to.
The sum of the first x odd numbers
Okay.
is equal to the sum of the first x minus 1 odd numbers plus the xth odd number. Xth.
Okay, so, okay.
What's the last one that you subtracted? That's the L.
Is that supposed to be an X or a K?
That's a K right there. That's an X. That's 2x plus 1.
Right, so why is the other side K?
2k minus 1 plus
Oh, okay, okay.
2x. Did I not write like that?
No, you didn't, but.
Oh, sorry. Oh, that's supposed to be minus 1 right there. So we're summing up this thing, and then this is a term by itself. Maybe put that in parentheses too.
Yeah, okay, that makes sense.
Sorry, I don't know why I had written before. That's what I thought I wrote. So we took out the last thing that we would have added on. You with me?
Wouldn't that just be 1 though? Or a negative 1? No, I'm wrong, never mind.
Okay. So,
Okay, we're good.
it's all looking good now? Okay, now we already know what this thing is. Right? Look at the line right above it.
Oh.
We already know what X
X
minus 1
minus
is.
1 squared plus 2x minus 1.
Wonderful! That's an equals.
No.
No?
That thing equals x minus 1 squared.
Okay.
That thing and that thing are the same thing.
Yeah.
Okay.
Good?
Okay.
And then a little bit of algebra. You multiply this thing out, you get x squared minus 2x plus 1. And then we got plus 2x minus 1.
No.
Alright. X times x, x squared. X times negative 1 times x minus 2x. Negative 1 times 1 plus 1 plus 2x minus 1. Oops. Minus 1. Which equals x squared. Uh-huh.
Oh, okay.
Contradiction.
What?
The sum of the first x odd numbers equals x squared. Remember,
Therefore, that's true.
x was the smallest thing that made the statement false.
Okay.
Okay. Let's, from the top. We got too caught up in the algebra. I think we lost track of the big picture. Okay. Oh, wonderful. Okay. So we're showing that the sum of the first n odd numbers equals n squared.
Okay.
That's what we're trying to prove. We're saying let x be the set of all the numbers, the natural numbers, where that's not the case.
Okay, so I just really quick question. I know that when I plug in numbers, 2n minus 1 goes there. Like I've already plugged in the numbers for the examples, but how did we get that in the first place? So does that make sense at all?
Are you saying how does this generate odd
I'm
numbers?
saying for 2n minus 1 plus 3 plus y all the way to 2n.
Oh, maybe I should have done this.
How did we get to 2n minus 1?
That's the nth odd number.
That's
Yeah,
the
but
last
why?
number.
I'm sorry, I'm not drawing conclusions.
Because it's an odd number.
It shouldn't be
2
possible.
times
Okay.
No.
Maybe this will help your thinking.
Oh.
2n is the nth even number. There's its odd counterpart.
Oh, okay.
Right. Maybe that will click something. If you think about the first even number as 2 instead of 0. I don't know.
So wouldn't you have to say where n is not equal to or something? Or where n is not equal to 0?
N greater
Oh,
than
there it
0.
goes, okay. Yeah. Okay.
Okay,
Alright.
so we're back to understanding the formula again.
I thought I was doing so good.
The sum of the first n odd numbers is equal to n squared is what we're proving.
Yeah.
X is the set of all natural numbers greater than or equal to 1 that don't make that statement true.
Right.
Assume, by way of contradiction, that x is not empty. We know that x is empty. We know that every natural number greater than or equal to 1 makes that statement true. Assume, by way of contradiction, that it's not empty. If it's not empty, then it has some least element x.
Right.
If it has some least element x, it's not 1 because we know it works for 1.
Okay.
So it has to be greater than or equal to 1. Or sorry, it has to be greater than 1.
Right.
So x minus 1 is a natural number greater than or equal to 1. So x was the smallest number that made the statement false. So x minus 1 makes the statement true.
Right.
And since x minus 1 makes the statement true, then x makes the statement true. Contradiction.
Contradiction. Okay. That makes sense now.
Big picture what you do. Assume that there's some number that's the smallest number that makes it false. Use the fact that a number is slightly smaller than it makes the statement true to show that that number also makes the statement true. I don't know. You already need a break.
It's already 2.
Got an hour without water.
I didn't drink any water.
Alright.
You guys are denying that? Wow.
Pretty brutal, huh? Let's see. By the way, I strongly recommend reading the author going through all the stuff. He tells about it in a completely different way than I do.
Because that would help us, huh?
Getting multiple perspectives, I think, would.
Maybe. If he was here teaching us.
Well, the way I came up with my ideas was reading what the author had to say. So, I don't know why that's such an optional thing in high school kids' minds. So, do I want to read my textbook?
My quick question, just to make sure I'm on the right track. For step 7, we kind of show that if you were to take that, it would make it true, right?
We're showing, on step 7, we show the fact that it's true for x minus 1 implies that it's true for x.
Okay, alright, because we do that by taking out the last, we did by taking out the last one. Okay.
Yeah, see, we've never even heard of that. Taking out the last
Yeah,
one.
we did, at least, I don't know about you guys, but last year when we were in college, algebra 2, I worked very little with Sigma. I
Worked very little with it.
Yeah, like we used it, but not very much, so I didn't get a lot of practice with it.
Yeah,
And by the end of the year, I totally forgot like what it was. So
It's just notation. It's just adding numbers. I don't know. It's weird till it's not. And it's just another shorthand.
yeah, I know.
Kind of like using by way of contradiction, BWOC. Shorthand for writing a song. Shorthand for not writing out words. Alright. Oh, that's proof template. Next proof. Next proof. Yeah. Don't you want to get comfortable with this?
You probably need to do this all day to understand it. So
I know.
it's almost gonna be true.
Curtis, where am I mistaken?
Let A not equal to 0. And you've probably seen this before. Sum of a geometric series. Let me rewrite that. So let's go over what we're proving real quick. So n is just some natural number, okay? And we're saying that as long as a is not 0, the reason we don't want a to be 0 is we don't want to handle 0 to the 0. 0 to the 0 is undefined. And we don't want a to be 1 because in our formula we're going to divide by a minus 1, and we don't want to divide by 0 because that's undefined. So that's why we're saying a can't be 0 and a can't be 1. So as long as n is a natural number and a is any real number that's not 0 and not 1, then the sum of a to the k from 0 to n is equal to this.
Huh. That's cool.
It is cool.
Okay, prove it.
Okay,
One.
and guess what we're going to use to prove it?
The proof we just said.
Smallest counterexample.
Smallest counterexample. So what's my first line?
Let x equal n equals n.
Set of all natural numbers such that
A is not equal to, A is greater than.
such that the sum from k equals 0 to n of a sub k is not equal to
Is that
a
a
to the plus
to the
1
power of k?
minus 1 over k minus 1.
Where A is greater than, did you have to say that?
But, yeah, okay.
Where a is not equal to 0 and 1.
Yep.
Good?
Yes.
Next step.
Assume BWOC that x is not 10%.
Perfect.
And then by WOP.
By the well ordering principle.
X contains some least element little x.
Okay, now,
Observe that x minus 1 equals that. X minus 1 makes
we want to make sure that x minus 1 is still a natural number, right? This is a statement about all natural numbers.
Right.
We want to make sure x minus 1 is still a natural number.
So you have to make sure that x is not 0.
So we need to make sure that x is not 0. So observe that a to the 0, which is equal to 1, is equal to a to the 1 minus 1 over a minus 1.
So x pretty much represents anything. Little x.
No.
It represents exactly what you said. It's the smallest natural number in this set that makes the statement not true.
Can we,
1 makes the statement true. Or sorry, 0 makes the statement true. When I plug in 0 here, I get the same thing that I get when I plug in 0 here. Right? Look,
Okay.
evaluate
Which
this.
one's the smallest one?
Evaluate this left-hand side for n equal to 0.
Okay.
Right? So from k equal to 0 of a to the k is just a to the 0. That's right there.
Okay.
When you plug in 0 for n here, you get that. They're both equal to 1. So they're equal to each other. So 0 makes this statement true.
Okay.
So n can be 0. So x must not be 0. Because x is the smallest thing that makes the statement
X
false.
has to be smaller than 0.
It has to be bigger than 0. There are no natural numbers smaller than 0. We know that x is a natural number that makes the statement false. 0 makes it true. So x has to be bigger than 0.
So 2.
It could be 2, it could be 1, who cares? So we know that,
Oh, x is not 0. Right, okay.
we know then x is not equal to 0, which gives that x is greater than 0, which gives that x minus 1 is greater than or equal to 0, which gives x minus 1 is still a natural number. All we're trying to do is make sure x minus 1 is still a natural number.
Okay, right.
All right, so now x minus 1 is a natural number smaller than x. What does that tell us?
That x minus 1
That
works.
Oh, I know this one.
Works.
Yeah.
So then, plug it right in. So then the sum from k equals 0 to x minus 1 of a to the k is equal to a to the x minus 1 plus 1 is just x.
Those two groups are super similar.
Minus 1.
Yeah.
They're all going to be similar, very similar every time you prove it. So then, sorry, I forgot my then.
Equals that, okay.
So then that equals that,
Right.
right?
Yeah.
7. Then the sum from k equals 0 to x of a to the k is equal to the sum k equals 0 to x minus 1 a to the k plus a to the x.
Could we take just a quick second and explain, just do an example, like I see what that's saying, but can we do like a couple examples just to
What do you mean?
make it
Oh, you mean of this
Yeah.
being, sure.
Or maybe tell me like what it's counting, like what's the
Sure, yeah, let's do an example real quick. Alright, so let's look at the
it's like
sum
the formula makes sense, but I don't.
from k equals 0 to pick a number.
5.
5 of, pick an a, can't be 0, can't be 1.
It's just 8.
3.
Well, we're gonna, you pick a number, 3.
2 minus 1.
3 to the k. So we're gonna sum up from k equals 0 to 5 of 3 to the k. Now what we better get, let's calculate what our answer should be according to this thing. According to this thing, we should get 3 to the 6 minus 1 over 3 minus 1. Right?
Right.
3 to the 6. Well, crap, that's huge. We're not going to be able to do this in our heads. Let's tone down a sec and just put that to 2. Let's make that a 2. Keep it simple. So, 9 minus 1 is 8, divided by 2 is 4.
4, okay.
Now let's check here. So this is equal to, plug in 0, 3 to the 0 is
1.
1, plus plug in 1, 3 to the 1 is
3.
Oh, I see.
3.
Oh, and there's only 2.
Oh, I messed something up.
No plus another.
This is supposed to be a 3 down here. It's m plus 1. So sorry. So sorry. 3 cubed is 27, minus 1 is 26, divided by 2 is 13.
Okay.
Okay, now let's continue. So we plugged in 0, we plugged in 1, now plug in 2.
That's
9 is equal to 13. Ah, magic, it worked.
13.
So basically you're saying those two are equal, not whatever you plug in will equal that.
Can we do it for 3?
They're always equal is what I'm saying. For 3
4
here.
and equals 3, yeah.
Sure. So if this happened to be a 3, let's switch this to a 2.
Okay.
So this is 2 to the 4 over that. So let's see. 2 to the 4 is,
16.
minus 1 is,
15.
divided by 1 is
15.
15. Now let's calculate this. Alright, 2 to the 0,
Is
1 plus 2 to the 1,
2.
plus 2 to the 2,
4.
plus 2 to the 3,
8.
8, which is 15.
Okay. So, like, okay. And that makes perfect sense.
So that's what we're proving. We're proving that for any real number A, as long as it's not 0 or 1.
I'm trying to see what it's proving, like, combinatorial. Does that make sense? Like, what is it counting? Trying to think.
Oh,
That's not counting.
what it's
It's
counting?
like, it's weird, but maybe, it's probably not just me, but
I
it
get what
seems
you're
like
saying,
when I
though.
know what it's counting, it makes a lot more sense.
This has a fairly easy algebraic proof.
Yeah.
So maybe I'll show you that real quick.
Okay.
All right. Let me make sure I get this straight in my head because I always screw it up. Let's see. So if I have x minus 1 times 1 plus x squared plus x cubed plus dot 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 plus x to the n. Okay? What does this equal? So let's multiply it out.
I feel like we must be reading somewhere to that before.
We've done this exact thing before.
Okay.
Distribute the negative 1 through. We get negative 1 minus x squared minus x cubed minus dot 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 minus x to the n. Distribute the x through. We get positive x plus x squared plus x cubed plus dot 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 plus x to the n plus x to the n plus 1. Everything goes out. Over here you're left with x to the n plus 1 minus 1.
Why did we put to the n plus 1? Probably just to the n. Oh no, we're good. I got
X times x to the n, you get x to the n plus 1.
Right.
Okay, so this, now I may use some of our notation. So let me rewrite this another way. X minus 1 times the sum from k equals 0 to n of x to the k is equal to x to the n plus 1 minus 1.
All right.
All right, and then finally we get the sum from k equals 0 to the n of x to the k is equal to x to the n plus 1 minus 1 over x minus 1.
Oh.
Which is exactly what we're proving.
All right. Okay.
So, there's the proof, but now let's go back to our more convoluted way of proving it.
Yeah. Why would we prove it this way when we can just do that?
And the point is to introduce cases that you're already comfortable with, to get you comfortable with the way it's proved.
Yeah. Yeah.
Okay, so, where were we? Okay, so then the sum of all the terms up to x is equal to the sum of all the terms up to x minus 1 plus the x term, right?
Right.
Which we already know what this is. What's this?
At k equals 0? What do you mean?
No, this whole term right here.
Oh.
That's this, right?
Yeah.
So this is equal to a to the x minus 1 over a minus 1 plus a to the x. Get common denominator. So that's equal to a to the x minus 1. A times a to the x gives me a to the x plus 1. Negative 1 times a to the x gives me minus a to the x, all over a minus 1.
And you just, okay. Yeah.
And then cancels out. So we're left with a to the x plus 1 minus 1 over a minus 1. Contradiction. That means the statement's true for x, which can't be. We'd rather show that the sum from k equals to 0 to x of that equals that. X was the smallest thing where that wasn't the case. And it turns out that was the case.
Right.
Doesn't work. We follow that?
Mm-hmm.
Therefore, big X is empty. In other words, therefore this was wrong. And therefore the statement is true for all natural numbers. Alright, got 2 more proofs to do. I'm not sure how much of the board that camera actually captures.
Yeah, 'cause I'm sitting right here.
It cuts off a good chunk. Maybe we'll go ahead and go on break, and I'll erase all this and get started with the next verse.
Okay. Let me take a picture of the board. We're on my computer because I know that I'm going to forget all this, and the resolution isn't great on YouTube.
Yeah.
Yeah.
I don't know why none of this makes sense. I mean, not none of it, but. Like, the first homework problem that we have,